Hi there! You are watching a video of above-ground storage tanks in industrial plants. The failure mechanism of a tank subjected to external pressure is different from the failure due to internal actions. Failure due to internal actions can be understood as failure of the tank due to overstress in a part of the tank, exceeding the allowable stress of the material. Meanwhile, for the case of external pressure, the tank cannot support its geometric shape anymore. Suddenly and irreversibly collapses, adopting a new configuration of smaller volume. Unlike tanks that are only designed for internal actions, there is no single formula or unique design equation that suits the condition of external pressure. Instead, there are several options available to the designer that can deliver an adequate design. Annex V provides the minimum requirements for tanks that are designed to operate with external pressure, that is vacuum, as normal operation condition. The scope of this annex applies to tanks subjected to uniform external pressures in the range from 0.25 to 6.9 kilopascals. When the values of external pressure are within the range mentioned, the design of the three main components of the tank must be checked. This is roof, shell and bottom. The shell of the tank is the most critical element for the external pressure verification. The calculation process to determine if the tank shell is capable of withstanding the effects of the external pressure is the following. First, calculate the shell thickness as per hydraulic and internal pressure. Second, check the elastic buckling condition, elastic zone of the material. Third, find the total transformed height. And fourth, calculate the allowable external pressure in the tank shell. To apply the verification method developed in Annex V of the API 650 code, the following criterion must be met, where D is the diameter of the tank, HTS is the total transformed height, Fy is the yield strength of the component operating at higher temperature, Ts minimum is the thickness of the thinnest shell course of the tank, E is the modulus of elasticity of the material. If this criterion is not met, the external pressure check must be carried out according to the ASME 8 Division 1 code for pressure vessels. The vast majority of storage tanks are designed with shells of variable thicknesses, thicker courses at the bottom and thinner shell courses at the top. To evaluate the effects of the external pressure on the tank shell, it is necessary to unify the thickness of the tank shell courses and find the new total tank height. This is achieved by transforming the height of the shell courses as a function of the thinnest shell course as shown on the screen, where HTS is the total transformed height, H1 is the height of the thinnest shell course, TS1 is the thickness of the thinnest shell course, H2 is the height of the second shell course, TS2 is the thickness of the second shell course. Once all factors described in previous sections have been considered, the allowable external pressure must be obtained. The allowable tank shell external pressure must be greater than the external loads. The procedure is shown on the screen, where d is the tank diameter, HTS is the total transformed height, Ts min is the thickness of the thinnest shell course of the tank, E is the modulus of elasticity of the material, and C is the stability factor. If the tank shell allowable pressure is smaller than the acting loads, the tank shell moment of inertia must be increased. In other words, stiffening rings should be used. When the tank shell is not able to withstand the effects of the external pressure by itself, it is necessary to increase the moment of inertia of the tank shell. The moment of inertia of the tank shell can be increased in two ways: increasing the thickness of the shell courses, obviously this is only recommended for small tanks, and adding stiffening rings. This is the common practice to increase the moment of inertia of the tank. The maximum spacing between stiffening rings is determined according to the following: where d is the tank diameter, Ps is the allowable external pressure, Ts min is the thickness of the thinnest shell course of the tank, E is the modulus of elasticity of the material, C is the stability factor, HTS is the total transformed height. If H safe is greater than HTS, no stiffening rings are required. The number of rings required, Ns, shall be calculated according to the following equation, where HTS is the total transformed height and H safe is the maximum spacing between rings. The result must always be rounded up to the next integer. The moment of inertia required for the combination of tank shell plus stiffening rings is determined by means of the equation displayed, where erect is the moment of inertia required, Q is the radial load imposed on the ring by the shell, and 2 is the number of theoretical buckling waves. A profile with a moment of inertia higher than erect must be selected. The required cross-section of the ring is calculated according to the equation on the screen, where A rect is the ring cross-section required, Q is the radial load imposed on the ring, and Fc is the compressive stress of the plate. A ring with a cross-section higher than A rect must be selected. As indicated earlier, rings should be located on the tank shell according to the thickness of the shell courses. Rings will be closer to each other in those areas of thinner shell courses and more distant to each other in sections of thicker shell courses. The required moment of inertia must be provided in all regions of the tank. The design of stiffening rings on the wall of the tank for both loads, wind pressure and due to external pressure, must be carried out jointly. Although it is true that the requirements are different for these two conditions, the design must be carried out with a global vision of the tank.